All right, hi everyone. We're the last talk, so I don't blame you if you want to walk out. But if you do stick around, I will tell you a little bit about lightweight formal methods. So my name is Jan. I am head of L2 scaling at QuantStamp. It means I'm usually involved in a bunch of things like scaling solutions and the security of those systems. But I have an academic background in a lot of things. But one of the things I like to study is formal methods, lightweight formal methods. And as a security company, it's sort of a natural fit. And today, I just want to talk to you a little bit about what lightweight formal methods are and how they relate to Web3. So it's a bit of a survey, a bit of an introduction. It's technical in the sense that I'm going to drop some buzzwords, but not technical in the sense that there's any math on the screen or any proofs. There's no code, nothing like that. And then the sort of second half of the talk is sort of like a call to action. So if you're looking for something to do this weekend, at the hackathon, it's a particularly good topic. So first I'll give you a quick introduction, and if at any point you want to download the slides, the link is there. It'll be up throughout. So why do we care about formal methods or security? Well, I think the obvious answer is that people have gotten screwed pretty hard here in this space, right? These are some headlines that are kind of recent. I think there's some older ones. This is stuff goes wrong all the time in crypto, and this is true in sort of the public sphere, and it's very common in sort of everyday knowledge that crypto has kind of got some risks, in part because of these hacks, but it's also been studied academically, and there's a lot of work going into trying to figure out how to overcome these issues, to learn from them and never make sure it goes on again. And unlike other software development sort of areas or domains, crypto is actually pretty good at adopting some really strong tooling for this, which generally is referred to as formal methods. So it's a way to prove, mathematically that some properties of your system hold. And I'm not going to go into a very formal definition about that, but if you've been in the space for long enough, you've seen, at a bunch of conferences, people will regularly get up on a stage and say, here's how to sort of prove something. They can't show the whole thing usually because it's a very complicated process, very slow, it requires a lot of expertise. But things like theorem provers, static analysis tools, symbolic execution things, and even linters are really prevalent in this field, more so than other fields. And this is largely in part to the fact that you deploy a smart contract on Ethereum or most other blockchains, you can't change them. They're there, they contain a bug, and if they contain lots of crypto, someone's going to try to exploit that bug in order to take the funds out of that contract. So to prevent this, you want to be as sure as possible as you can be at the beginning of the deployment. So prior to hitting deploy, you try to prove that everything is correct, and that's the dream. It's nice, in some settings it definitely can be done. In crypto it's a little bit easier too because you have bounded execution, right? A transaction cannot run indefinitely long on Ethereum. You have a gas bound, and therefore a number of steps it can take. And so the search space of proving, if there's a counterexample is also shrinking. Doesn't mean it's easy. It doesn't mean it's sort of quick. In fact, most of the time it's still very expensive and very much requires domain expertise. Usually you have people with PhDs, sitting down with you and saying, here's how I'm going to model your system formally, and here's the property I'm going to try to prove, and then they're going to go put it into some custom language that you probably never heard of, and then they're going to come back with a result saying, actually you have a bug here, or actually we think it's fine. There's a lot of caveats there though, because even when they do that, that's a manual process, more or less, like most of the time. There's some tooling that can automate parts of it, but if they get the specification wrong, they've just proved something wrong, and that's not ideal. So it's very important. Oh, I think I gotta, be more active. I need a password over here. Sorry. I'll click through much more quickly. Yeah. So typically, these systems are still out of reach of the average hackathon participant, and maybe even the average DAO, because they're really expensive and they're really slow to do this. So you can hire out, or you have to hire you can hire a firm, or you have to hire an expert, and experts are expensive. So what I'm trying to say is that's great and it's really helpful, but we also want to capture sort of the less experienced and less technical people in this space. And one way to do this is we can add this keyword lightweight in front of the formal methods. And here the goal is not to formally verify that the entire system is correct, but that very specific functions and properties hold. And so you're going to abstract away a lot of the system, and you're not going to prove everything is totally secure, but maybe you'll be sure that actually there's only one way to withdraw something from your contract. And if you can do that, that would be great, because then maybe there's a whole lot of other bugs, but no one's going to rug pull you, or no one's going to like exploit the funds. And that would be great. And to do this, we want to leverage a whole bunch of tooling from the software engineering community. Usually there's tooling that's based on SAT solvers and SMT solvers. I'll talk a little bit about sort of the high level of how those have been applied, but not define them, unfortunately. And they work by just reducing the problem to something mathematical, and it's a very bounded, so they won't prove arbitrary execution. But because blockchains are limited, the transactions are small in size, it's often good enough. You've probably already seen tools like this, heard of them. There's another slide coming up where I'll list some of them that you may have seen if you've been in the space long enough. And I think it's what I'm trying to say is that really this is the approach to take, because while proving everything correctly is very, very nice and expensive, very nice and great, it's also very expensive. It would be great if everyone could do it. It'd be great if everyone could learn it. It'd be great if everyone could take advantage. The reality is people won't. And so why not leverage the tooling that the community has already kind of built? Again, this will come up in a slide, and do this in only small bits. And you can even like decentralize parts of this verification if you really want to. That would be a technical problem, but you could spread the work out, and most importantly, you could make sure you're sure of certain things that your users really, really, really care about. And although we've started taking advantage of this in the Web3 space using smart contract analyzers and things like this, I'm going to show you that there's a whole bunch of other places that we can use this, and this is probably a great place to hack on something if you need ideas. So before I go any further, I said I won't define formal methods. I probably should have, but I didn't. I will definitely define lightweight formal methods very precisely. So what I want to say is that develop things small and incrementally. Care about the properties you want, and this is a definition from Daniel Jackson. He's a professor at MIT. He's been doing this type of work for 2012. He's got a great book on some tooling. But just focus on the parts that matter in your code. So don't try to prove the whole thing. In the same way that when we get an audit as a security company, most people don't bring us their front end, because if the front end sort of goes wrong, you can fix it. And that's totally fine. You can't change the smart contract. In this pure smart contract sense, there's probably also parts of the smart contract that maybe don't matter quite as much as some other parts, right? There are probably some convenience functions, there's probably some view functions. There might be some things that, are nice to haves, but if they go wrong, your system's not gonna break and your users aren't gonna be totally upset with you. They'll just be annoyed. And obviously you don't even want that, but one is definitely better than the other, right? Being annoyed is better than being, really, really angry at someone. So don't throw away the tooling, don't throw away all the math, but just focus them a little bit. Get them down to a scope where you can do it in a couple of days or hours. And that would be really, really great. And it won't prove everything, but you'll be able to find very, very local bugs. And this is great because you're still making quality improvements to your code. I mean, we see things all the time where we don't have even specifications or tests. This is still well beyond that. You probably need those things first. But even just proving that particular behaviors work, right? I was talking about specific paths like withdrawals. This would be the place or technique to use it, right? So you don't have the whole system necessarily working as function, but you have one property. And then once you have that one property, you can also consider the next property. If you have withdrawals, well, now also check deposits and see what happens. And if you can do this at a level that's more abstract than the code itself, you can actually get a lot of wins from the tooling. I don't have the numbers here to prove it to you, but really what would be great is looking at the specification. Because often we get, most of the bugs we find in client code is not reentrancy, it's not, math errors. We see those sometimes, probably often. But what we really see is people thought they wrote a dApp that does something, and then it doesn't do that for one reason or another. Either because their specification is wrong or because there's some conflicts at the end of the day. And while some testing will catch that, if you can prototype that really quick at the specification level before you write code and say, look, I have two features and one of them is going to conflict with another or with the other, then just don't build it. And now you've saved yourself a whole bunch of development time. And if you can do this in 3 or 4 hours, you've possibly saved yourself hours of auditing time, not to mention, days of development time potentially. And when you get to an audit, you also have additional artifacts to show your people that actually we knew what we were doing and we know what we want you to be doing. So this would be great. And this turns out to be less costly, and often it can be more accessible. So Bear with me as I'm still flying at 1,000 feet here, but I'll give you some examples right now. Most of this will come in the form of symbolic execution. You've probably seen some tooling for this already if you're a developer. If you're not a developer, you can check these out. Reentrancy was a cause of major issues, so there's a lot of tooling to capture exactly that. Right? And that's a good starting point because that's a nice property to be able to prove and say, oh, I have no reentrant functions. And there are tooling to catch this. So, there's a bounded model checker, there's Manticore, Ante, Slither's really good. So there's probably one of the best tools out there to catch things. And probably all three of those except Slither, the first three, use a SAT solver. So this is sort of a general purpose mathematical solver at the end of the day. And it works, but it doesn't give you a proof. It doesn't say this will definitely never happen. It just sort of says, I didn't find it now or I timed out. And usually that's good enough. If your program's small enough, it will give you an actual proof, but typically, for a complicated D5 protocol, it's not going to do that. Depends what you're trying to prove, though, of course. But these tools exist, and that's the point. Most of them are non-trivial to use. So there's usually push buttons, so you can probably download that, yarn install or whatever, and I think it just works out of the box. They've done a good job. I haven't actually used the bounded model checker here, but if it's a bounded model checker and you're writing your own properties to prove, it's going to take you a little bit more time. Doesn't mean it's not worth considering. And like I said, the goal is really trying to use this in addition to your other things. So what you want to do is, make your test as good as possible. It's always difficult. No, it's very rare that we see clients that come with 100% test coverage because most protocols are very, very difficult. And so instead of, trying to capture 100% test coverage, you can spend resources somewhere else. Because often when you're writing a test suite, you have diminishing returns on getting that last 5, 10% in coverage. The first 80% is really easy. The other ones are much more difficult, or you got to mock up things, or things need to be in very specific situations that you're almost coding for and expecting to never happen. But you would like to have some assurance of that. Writing a model for your specification for those corner cases might help you do that a lot quicker. And because most of them are almost push button, but not quite, it's less time, right? So if you can learn how to write a test suite, you can probably learn how to do this. It might take you a little bit longer. You might not see the value at front, but if you start to see, how it can guide your development, not just your sort of correctness checking, you might actually really like to love it. And more importantly, you can help contribute to the ecosystem with these tools. So these tools are often built at hackathons exactly like this, or they're enhanced, or you can do things like formally model other systems at these hackathons. And I think that's really, really interesting. So there's not a lot of dApps out there for which you can say, what is this actually doing? What's the specification? There's probably a couple. I think Maker does this. But most of them, when you look at the code, you don't know what it does. So unless you're willing to sit down and read all of their Solidity code and maybe their documentation if they have some, it's really painful. But if you can do this exercise, even as part of a hackathon, then you could also check its correctness, and you have additional documentation that your users can read. And if you target the specification level, you're doing it in such a way that no one's reading variables of a specific type and size. It's just, here's the flow of what's supposed to happen, and here's a variable, and they don't need to be specific. I'm sorry, I was just about to hit the next slide.
I need to work on that.
Yes. Okay, great. So how can we actually do this? So I've already hinted at one thing, which is building this type of tooling and process into your specification design. You still have to take a lot of my stuff at face value, but what else can we do? So first I want to caveat this with, no matter what you do here, it's not going to be a silver bullet. It's going to take time and effort, and it's probably not going to be a push button solution that works for every dApp everywhere, and certainly it's going to be not a silver bullet, right? So you can't just say, I spent 4 hours writing my model, why isn't everyone convinced my stuff is correct? It's not going to be the case. You're still going to need those tests, because if your model is too far removed from your code, it's not a very helpful model. Ideally, it's close enough that it's meaningful, but far enough away that you can prove something useful on it. And you'll still need code audits, because both of those things can still go very much wrong, and therefore you want to be sure, absolutely sure, that you've got everything. So audits and tests are still absolutely critical. But since tests maybe guide your implementation, and audits are definitely the last line of sort of defense for most people, because they come when everything is developed. Doing this type of exercise helps get security from the forefront, right? So from the very first thing you do, you can be more sure that your application is going to do what you want it to do. And then when you go to get an audit, like I said, you do get one extra piece of artifact to share with them. And so, can we use these methods to do better? Absolutely. And do we need to? Mostly, yeah. If you write me an implementation of an ERC20 token, if you're still building tokens, just tokens, that probably doesn't need to be modeled. I think everyone studied that interface well enough, and it's pretty simple these days. If, on the other hand, you are doing something very new with bridges or DeFi or rollups or whatever it is, where you have lots of moving parts and lots of variables that you can't track, you need some level of abstraction anyways, right? Most people can't just spec out a rollup on a whiteboard. No one can do that. What they do is they draw components and they draw lines between them saying there's interactions and flows. That's just the model, right? So if you do that model slightly more formal, that's where you get these wins. And if you do this, you can do that feature interaction that I've talked about. The existing tooling that this ecosystem's already using has been shown to do this in other areas of software engineering. So there's a call to action here to just read those papers, which are kind of dull. Software engineering papers are not exciting. Bring those over to Web3. You can get a new analysis tool very quickly. Is it going to solve everything? Absolutely not. But if you can prevent one $500 million hack, you're doing the ecosystem a great job or great benefit. Alternatively, you can look at other things. So things like software product lines. What we're seeing now is that everyone is building one piece of code, and then they want to deploy it, everywhere. Or at least that's the sort of claim and joy of EVM equivalent rollups. You build one piece of software in Solidity, and you say, I'm going to put it on zk Sync, I'm going to put it on Scroll, I'm going to put it on whatever I want it to be. As long as they take my Solidity, it should be exactly the same. But there was a talk at L2 Warsaw, L2 Warsaw yesterday, where we saw that actually everyone treats opcodes a little bit different, more or less. We haven't really reached exact equivalence. Maybe there's one chain or two chains that do it, but a little bit of a change can have a big impact on how your code is run. So you write it, you expect it to be exactly the same, but it's not the case. So instead, you could build your software in a way that it's a product line where a feature is supporting, zk Sync or supporting Scroll or supporting whatever it is. And then, I'm so sorry. I need you over here. Sorry, I'll just try to keep touching it. It's almost done anyways. So if you build it as a software product line, then you can catch these bugs right away. And you can have actually your code configured by these tools. So you write a library that's like, this is my withdraw method that definitely works on zk Sync. And over here is a withdraw method that definitely works on I don't know, Scroll. And you have the system to configure which import to import inside your SDK. That's also really cool. Big companies do this all the time. Companies like auto companies and telecom companies, they do this all the time because they have to deploy on a whole bunch of different, specific sets of hardware, depending on, say, the car, and different user configurations. Why don't we start doing that? Like, why is everyone still just building it once and assuming it's going to work all the time? It is the pipe dream, that's nice, but I also think that in 5 years, we're going to have a whole bunch of chains that don't look like the EVM at all. They're going to have their own stuff, right? We're seeing things like RISC-0 come up. People are going to want to deploy the same code elsewhere. It's going to require different languages, or at least different implementations within the same language at certain times. So to get into this practice now, if you've got nothing better to do, this is great. This would be absolutely good. And the last benefit we get from targeting specifications and product lines and all this sort of high-level abstractions very quickly is that it scales a lot better, right? You can look at 100 models, which now each model might represent, some implementation of 200 to 500 lines of code, and suddenly you can reason about that. Whereas, reasoning about 100 times 100 lines of code inside of a solver directly might not be possible. So you get scaling benefits, which is really, really nice. And so I've already said, yes, some people can do better. We can also do better in other ways. There's been existing research that shows using these tools, you can generate test case automatically. Wouldn't it be great if you wrote Solidity and you just had test case automatically spit out? Are they going to be perfect? Absolutely not. I don't think there's any research out there that says they're perfect, but I haven't seen this at all in Web3. Please correct me if I'm wrong. If you know of a library that does this, by all means. But the same type of underlying ideas and technologies can be used exactly for this. So this is even more straightforward, perhaps. If you can build the tool, which is not going to be trivial at all. This is, it's a big task. Generating test cases automatically would save a lot of people a lot of time, right? It would be helpful. And then they just have to go refine the test cases and make it better. But it's still better than nothing. So Again, borrowing ideas from other places. And then once we get to that point where we have all this nice tooling, which would be nice, and it's probably going to take a couple of years, but I'm here dreaming, and I want to inspire you guys to be dreaming. We can also, go the other way. So this is us borrowing. Previously, I was talking about how we are borrowing a lot from the software engineering community. And I think that's really good, and we shouldn't discard those ideas. But once we know how these tools work in our domain, we can start going back the other way too, right? We can start saying, here's how you model things really nicely, and here's how you get specific operations in these tools to work a lot better. And when you do that, you contribute back to how these tools can be optimized. And now there's a feedback loop where they develop an idea, we implement it, we get better techniques, we give it back to them, they improve on the idea, we develop better tools, and the process repeats. And eventually we have everything we want sort of in some reasonable sense. Again, we're probably never going to be able to prove full system completeness for a lot of systems, but in a lot of places we have really, really, really good tooling. And then, the next most popular thing probably other than NFTs is zero knowledge. So zero knowledge proofs are, massively complicated. Most people definitely can't do that on the board, even if you could do a roll-up. I know very few people, and most of them have PhDs, who can actually, grade up and write down the proof system and the constraints, or at least the structure of the constraints. They're so big and so complicated that here we don't have a choice but to use automated tooling to do this. If someone says, I've written a CIRCOM circuit, can you tell me if it's correct? I can look at the CIRCOM code and I can say, oh, I think it is. But if I don't trust that CIRCOM compiler, I'm actually not really sure that I trust the code at all. So I have to look at the code it outputs, but the code that it outputs is just a bunch of constraints, and I can't look at that because I don't have enough time in my week to do that, right? 2 to the 19 is also probably too much more than, my lifetime, or at least my work-life balance lifetime. So, at some point, you need to have automated tooling anyways. And one place that's really, really underdeveloped is any type of tooling inside a zero-knowledge proof framework. So we've developed one tool. There's a couple out there that are other. They require sort of fundamental sort of modules inside the tooling that I've been telling you about, these SAT solvers, SMT solvers. But at some point, we're going to need them because we won't be able to manually check zero-knowledge proofs, so why not start looking at tooling now? Which thankfully I guess we are, but we need a lot of help. There's a lot, and there's going to be probably a dozen more proof systems coming out in the next I don't know how many years, right? The number of papers for proof systems is already high, so as soon as some of them get really popular, we're going to see a lot of problems with detecting them with the existing tooling, and we're going to need help. And then it also means we're going to need a lot of help in improvements, so there's things you can do better. I promise you no math, but there's a little bit of math here. The idea that once we actually build these toolings, they need to be optimized, they need to scale. If you think scaling to, a million lines of code is hard, scaling to 2 to the 19 constraints is even harder, and you need to do, a lot of clever stuff. So if you're more mathematically inclined, this is also for you. But it's the last talk. I want to leave a time for questions because I'm sure I skipped a bunch of stuff and people have some questions. The community is already doing really good at formal methods. I'm not here to say don't do formal methods. If you can afford formal methods and your project is valuable enough to do formal methods, by all means do it. Probably don't need it for an NFT. If you're doing DeFi and you can afford it, absolutely. But there's a middle ground, right? There's a middle ground where if you're doing something that's only kind of valuable maybe or kind of complicated, you can do formal verification on just parts of the system. And when you do that, you drive the cost way down. You get your assurances way up because you still get some things proved, and it's going to be a lot cheaper. It's going to be a lot quicker. So I'm encouraging everyone to try these. Unfortunately, what I haven't given you is a whole bunch of tooling for this. I listed some things there. This is the call to action part, right? There's technical challenges, and a lot of the tooling doesn't exist. But if you have interesting, software engineering ideas to port over in this space, I think you will get so many users. It'll be, great. Then the challenge will be keeping up with the tech and scaling and all that. So I'll stop there. If you got questions for me and I don't get to you here or you can't think of them now, please contact me. And QuantSnap is mostly a security company, but occasionally we do some research and grants. So check out our grants from the Ethereum Foundation on the bottom right there. We talked about L2 Block Explorer APIs and L2 Security Assessment, which I talked about yesterday if you were here. So I'll stop there.
Great, thank you very much, Jan. Any questions?
We see that Quantstamp does a lot of things, but do you experiment somehow with AI in securing code?
We experiment. Yeah, I don't know what I can or should say. You know, it's a very new area, and obviously on Twitter there's like a whole bunch of things about, you know, let's just plug ChatGPT into something. The privacy concerns about that are not something that we take lightly. So, you know, I don't think we're uploading just code to an arbitrary thing where people are going to learn from our code. But we have been exploring different local stuff. We have some internal tooling, which unfortunately I can't show you, that uses some version of AI or another, or intends to in the future. So experiment, yes. Do we have a product for it? No, I don't think so.
Maybe you can say if it's mostly LLM based or it's some other.
Unfortunately, I'm not the AI guy in the company. If you send me a message, I can definitely, you know, ask you to someone who has way more experience in that. I think it's very interesting, but you know, you can only study so much in your lifetime, and I chose not that.
Great. Anyone else?
Hi. Can formal verification do or treat the economic attack vectors?
Yes. So we actually have a tool for that. We have a tool where we can formally model the system, and it's not my tool again. We got quite a few researchers where we have a representation of your DeFi protocol, and we can tell you if there's like a flash loan or other MEV issues. I don't know the numbers on the accuracy, but it's pretty good. We just launched it, so ask me more about that offline, and I can share.
Awesome. So if no one else has any questions, then thank you very much, Jan, once again. So see you tomorrow or on the party.